Hello, this is Peter Newman. Today's video is Fluent using watertight meshing workflow and resulting in a steady simulation of this device that has two inlets, one here and an outlet at the top of the pipe, and some swirl that happens to go to a pod on the bottom. And that's the topic. We'll get into it from the geometry and build everything till we get to this flow result. Here we have the geometry open in SpaceClaim, where we can see two fluid bodies, a body called pod and a body called top. And then there's a hidden body called body of influence, BOI, that we will use in the meshing workflow. You can see a purple line. That means that I've used the workbench share button to share topology so that fluid can flow through the two surfaces, but I can get data out of the cells in just this body, for example. What we need to do here is use the Groups tab to label some named selections, which is as simple as using the Select tool, and here we click a named selection and call that Inlet 1, and then there's an Inlet 2 over here. Create Inlet 2, and then there's an outlet up here. Outlet. It's good to get the spelling right because Fluent uses that, out-L-E-T, there we go, to create things for us. We'll also create the names of the two fluid bodies by using a filter to pick bodies. There's another technique which is just to triple click, but that body is going to have a named selection called top, and this body is going to have a named selection called pod, and that will do it. We will let Fluent figure out where the walls are, and that one of the walls is a part of a shared topology that is an interior wall. So we're going to save this now. So I'm going to just save it as a shared fluid bodies with named selections, and that's the file we'll import into the Fluent meshing workflow. So I can close this and go to Fluent with Fluent meshing as a standalone and import that geometry into the mesh. Well, I'm going to start the mesh program and tell it we'll use double precision and 4 cores. Okay, Fluent has launched in the meshing program, and we're going to go ahead and do a watertight workflow and import that geometry that we know is. I just went back to Workbench, and on the Geometry tab copied the location of the file that we want to import. So back to Fluent, and on the import geometry we can paste that file right there and import that geometry. Okay, the geometry is read in and it asks, do we want local sizing? And yes, we do. And the type of sizing is body of influence, and the size of the mesh is 0.15, and that's on the body of influence. Next, it will want to do a surface mesh, so we'll generate that, see what we get with the default min and max sizes it's selected for us. So it's come back with a maximum skewness of 0.93, which is not acceptable. So we don't want to go on to the next step. We want to come back here and insert a task called Improve Surface Mesh with a new target value. Click Improve. And that has come back with an acceptable surface skewness, 0.7. We don't really need this title down here, so we'll toggle that off. And in Describe Geometry, this is fluid-only regions with no voids. There is a wall between the two, and we don't want that to be a wall. We want that to be internal. We've already done shared topology, so we don't do it again here. We won't do multi-zone meshing. It recognized the group names I made in SpaceClaim. I just want to flip them to pressure inlets for the simulation. And the outlet is correct, so I'll update those. The fluids are correct, so I'll update that region. And I do want boundary layers, and this is for coarse Y plus greater than 30, and so I've calculated the first height wall, the wall of the first height cell, 0.08, and apply that to walls only. So we'll add some boundary layers, and finally we will choose poly-hexcore with default elements and go ahead and generate the volume mesh. And the program has finished running. The minimum orthogonal quality is 0.06. Probably can improve that. I've seen 0.1, which is the value I'm targeting when I used a smaller cell size in this body of interest region. So I might go back and edit that to improve the orthogonal quality. But if that was acceptable, we would be done here and we would switch to solution and start solving. But I can go back and add boundary layers, actually before then, where I added local sizing. I can revert and edit that step in the workflow and get a target mesh size of 0.1 and then update, and the pretty much just, if I click on this last step and generate the volume mesh, it'll say do all previous. Yes, go ahead. So I will see if we get an improved value from that. So the good thing is it's no labor to go back to an earlier step and then tell it to recompute to the end. The disappointment was it only marginally improved the orthogonal quality, and I know I've seen better numbers than this. Let's try inserting a new task. Improve the volume mesh. There we go. Cell quality limit. That sounds good. Let it do 10 iterations. We're patient here. And yes, allow smoothing. Quality improve min angle. I don't know, the orthogonal quality is the one that's bad, but I'll just say give it a try. Oh, and that's a winner. Here we go. Final minimum orthogonal quality is 0.15. That's nice. We will be happy with that and go and switch to solution. For the next step, I guess we will click the check as suggested, but I think it's going to be clean mesh, and then we will switch to solution. Yep, done. Checking. Switch. Yes. And see you in the solution branch.